Hi everyone, welcome to lecture 16. The objectives for this video are the following. After watching, everyone should be able to, number 1, define a physical quantity. Number 2, describe sufficient conditions in terms of functional relationships between physical quantities. And number 3, apply the inverse method of agreement to eliminate one of two functions describing sufficient conditions. So far, our discussion of necessary and sufficient conditions has taken place entirely in qualitative terms. In this video, we'll look at the relevance of this discussion in quantitative fields like math and the sciences. In those fields, statements of cause and effect, or statements of necessary and sufficient conditions, have been replaced by functional relationships expressed by mathematical equations. The idea is that an equation expressing a functional relationship between physical quantities expresses an infinite number of statements to the effect that this or that physical property is a sufficient condition for another. So to get a handle on all of that, let's look first at what a physical quantity is. Consider something like the mass of an object measured on a given scale like kilograms, as we use over in the UK. We make a factual claim about a state of a physical system when we say that its mass in kilograms has a certain value. And in this way, mass, measured that way in kilograms, is a relation between states of physical systems and real numbers. For example, if we say the mass of this tennis ball is 1 kilogram, then that is just the same as saying the relation mass holds of the physical system tennis ball and the real number 1. And saying that is to say no more than something like this. For every real number x, there is associated a unique physical property having the mass x in kilograms. So, a physical quantity can be seen as not one, but as an infinite family of physical properties. And the properties in such a family are mutually exclusive, which is a term we've met before, meaning that a physical system cannot have two different masses at the same time. And they are jointly exhaustive over the states of the appropriate type of physical system, which means that a physical system of the appropriate type in a given state must have some mass or other. Something of the wrong kind would be something like the colour red, which it doesn't make sense really to talk about the mass of. We therefore make the following definition. A physical quantity is a family of physical qualities, mutually exclusive and jointly exhaustive over the states of the intended class of physical systems, indexed by some set of real numbers. And using this definition, we can formulate physical laws in terms of mathematical equations. Consider this equation, for example, the simple equation y equals 3x. This equation gives a concise expression to an infinite number of statements. So here are some of those statements. If x is 0, y is 0. If x is 1, y is 3. And if x is 12, y is 36. Now in general, we see what happens. For each value of x, the equation gives a unique value of y. And we say that y is a function of x. It's important to notice that if y is a function of x, it does not necessarily follow that x is a function of y, and there's a question on the assignment for this week that will get you to think about that. So what does this all mean in physical terms when the variables of the equation, like x and y, represent physical quantities? Well, if the variables represent physical quantities measured on fixed scales, like mass in kilograms, then, as we've seen, each numerical value of a variable represents a physical quality, for example, having a mass of 5 kilograms. Mathematically, we say this: if a physical quantity q2 is a function of another, q1, then for every value vi of q1, there is a uniquely determined value Vj of Q2, such that whenever a physical system has Vi of Q1, then it has Vj of Q2. And all that is to say that having Vi of Q1 is a sufficient condition for having Vj of Q2. One can check that it fits the definition of sufficient condition that we've seen. So we can say the following when we view physical quantities as families of physical qualities. If Q2 is a function of Q1, then for every member of the family Q1, there is some member of the family Q2 for which it is a sufficient condition. Now, we've seen a lot of abstract notation on this slide, so let's look at an example that illustrates all of this. Consider Newton's second law of motion, F equals ma. Here F is the force acting on an object, m is the object's mass, and a is the object's acceleration. Now the equation establishes F as a function of m and a, in that each pair of values for m and a uniquely determine a value for F. So, for example, if the mass m of an object is 5 kilograms, and its acceleration a is 2 meters per second squared, that's just the units we use to measure acceleration, there's no need to worry about the squared thing here. Then the force acting on that object is 10 newtons, and again, newtons are the unit that force is measured in, there's no need to worry about the units here. Now, since we're still dealing with sufficient conditions, the fundamental principles we use to analyze Mills methods must still apply here. So how do they apply? Now notice that instead of one conditioned property, we have the family of conditioned properties comprising a physical quantity. And we call this the dependent variable. In the Newton's second law example, this is F. Now, we have a way of establishing for each member of this family a list of possible conditioning properties. And this is done in 2 stages. At stage 1, we construct a list of physical quantities whose values are likely to be relevant in determining the value of the dependent variable. And we can call this our list of independent variables. In the above example, this is just m and a. And at stage 2, we construct a list of likely looking functions which make the dependent variable a function of our independent variables. For each conditioned property, or value of the dependent variable, each of these functions determines one or more complex properties which are possible sufficient conditions for it. For example, consider the 2 functions f equals ma and f equals m squared a. Now, function 1 would make the following, among other possibilities, a sufficient condition for f equals 4, m equals 4 and a equals 1. And it also makes m equals 1 and a equals 4 a sufficient condition for f equals 4. If you substitute those values of m and a into f equals ma, then it will give you f equals 4. Now, what does function 2 make of these values? Well, substituting them into function 2, we see that function 2 makes m equals 1 and a equals 4 a sufficient condition for f equals 4 again, but function 2 makes m equals 4 and a equals 1 a sufficient condition for f equals 16. That's what you get if you substitute those values into function 2. Now, since f equals 4 and f equals 16 are mutually exclusive physical properties, they cannot both be present at the same time. And using this, we can use Mills methods to eliminate one of the 2 functions as giving the correct sufficient conditions. And the key is to use the inverse method of agreement. We only have to look for an occurrence where m equals 4 and a equals 1 because that's where the 2 functions disagree, and then to see whether f equals 4 or f equals 16 is present in that occurrence. All we're doing here is applying the inverse method of agreement. So if f equals 4 is a physical property that's absent when the properties m equals 4 and a equals 1 are present, then those properties cannot be sufficient for f equals 4, and so function 1 can't be the right function. On the other hand, if f equals 16 is a physical property that's absent when the properties m equals 4 and a equals 1 are present, then those properties can't be sufficient for f equals 16, and so function 2, which would give you 16, must be the wrong function. So the inverse method would rule it out. So, using the inverse method of agreement in this way, we can narrow down on the correct function. Now, just a word before we move on to another example. Although the mechanism for the elimination of the proposed functions is clear here, setting up the list of the possible functions in the beginning is quite difficult, and the goal there is to isolate the minimum number of relevant variables possible. Now, I won't say much more about this here. There's a little more discussion in the text of the difficulties that are involved in this. So instead, we're going to end by walking through one more example, this time with some questions from me, to make sure we're on top of this stuff. So here is another physical quantity, temperature, and let's say we measure it in degrees Kelvin. And suppose we're interested in coming up with an equation that relates volume V to temperature T and pressure P. So we hypothesize two functions. Function 1, which says V equals K times T over P, and function 2, which says V equals K times T squared over P. So here V is volume, T is temperature, and P is pressure. And we've also got this constant K, which isn't a physical quantity, it's just a number. And we're interested in which of functions 1 and 2 give the right sufficient conditions. So here's the first question. Have a look at the functions, and you might want to pause the video at this point and have some paper at hand. Copy them down in case you need to scribble to figure out the answer to the question that's coming in just a second. And once you've done that, move on to question 1. So we should have both where K equals 1 and T equals 1 and P equals 1, and where K equals 1 and T equals 2 and P equals 2. When we substitute those values in, we find that V equals 1 for both sets of values. So hopefully you've copied the functions down by now. If you haven't, rewind and do that, because the second question is coming up. So substituting those numbers in, according to function 2, K equals 1 and T equals 1 and P equals 1 is a sufficient condition for V equals 1. So here's the next question. Substituting those numbers in, we find that according to function 2, K equals 1, T equals 2 and P equals 2 is a sufficient condition for V equals 2. So here is the final question. The answer is to look for an occurrence where K equals 1 and T equals 2 and P equals 2. Remember, those are the values where the two functions disagree. So if we look for an occurrence of those values of K, T, and P, and we find out that V is 1, we can rule out function 2. And if we find out that V is 2, we can rule out function 1. Okay, so we'll leave that here and look ahead. Next time we'll finish off chapter 5 by looking at law-like and accidental conditions. So have a go at your reflection questions, and I'll see you next time.